power will be coming from the roadway. So we'll have this multiple chargers, which will be situated, let me get the laser pointer, which will be situated at certain gaps over this lane. And as the car moves over those, it will keep getting pulse of these charges and therefore keep getting charged as continuously as it moves. What it will do is that it can get then charged without having to stop. So that essentially reduces the charging time to 0. And next is that it always have a charging available. Therefore, at a time, it only needs to charge or store only a small amount of charge. Since at a time the storage requirement is reduced, the battery size can now be reduced. However, it's a pulse charging scenario where, of course, the battery health and lifetime, these are questionable things, and research have been happening on that. From an Indian context, if we think about, then this dynamic charging seems a bit of a far-fetched idea because the Indian traffic is a bit haphazard. So here we can actually take a relatively middle approach, what we call the opportunity charging, where you charge at the frequent stops. The frequent stops can be parking lots or scheduled stops where you stop for like a 15 minutes, half an hour, or maximum 1 hour or so. And if we can implement it in multiple places, what it does is that it gives you the option of a convenient charging every time you park somewhere. And therefore, you do not need to, again, store a lot of charge at a time, which reduces the battery size. But of course, it does not reduce charging time as such, but you do not need to charge a lot at once. That is the overall idea. However, of course, as with the wired EV charging, it needs an optimized distribution of the charging sources or the charging stations in this case. So with this approach in mind, I mean, we can actually give a relatively good example of it where, for example, let's say the delivery executives from different platforms, they would come to one of these apartment buildings, they would park their two-wheeler in front of the apartment building and will go and to deliver various goods at various apartments within that building. So they'll probably park there for 15, 20 minutes while delivering those goods. And if there is a wireless charger, they can just simply conveniently park on top of that, get certain amount of charge while delivering these goods. And then they go to the next apartment where they get charged again. Therefore, at a time, they do not really need to charge a lot. Therefore, the battery size can be smaller. Now, conventionally, the wireless charging has been happening using magnetic field, where we push a current through the transmitting side coil that was embedded in the roadway, which creates a time-varying magnetic field, which induces an EMF on the coil which is on the vehicle. And that's how we transfer the power. But the inductive charging uses a couple of things. One is lead wire to build the coils at high frequency. Another is ferrite slabs to be able to guide the flux and not let it go into the vehicle so that it cannot harm the passengers. So you can see from here these large ferrite slabs that are needed at 22 kilohertz. And this on the right hand figure, you can see an attempt to embed these charging pads into the roadway. These are not from India. These are from foreign countries where these attempts have been made. Now, the point is that ferrite is very brittle and ferrite, the presence, but it's heavy. The presence of ferrite makes the coupler heavy. Therefore, you are attaching something heavy to the vehicle. And it also makes it difficult to embed in the roadway because ferrite is brittle. So if we can get a solution where we can avoid ferrite, then we can reduce the weight of the coupler as well as we can make it easier to embed on the roadway. And with this promise that we were looking into a capacitive charging technique where we use electric field and not magnetic field to couple between the transmitter and the receiver side. So the idea is that there will be a pair of conductive plates which will be embedded on the roadway. There will be a pair of conductive plates in the vehicle chassis, under the vehicle chassis, and the electric field between the plates will couple the transmitting side to the receiving side. So here it's a typical example of one of these couplers, that how it will look like. These are the two copper plates embedded in some sort of insulator. One of the properties of this insulator will be that they need to have a high voltage breakdown strength, because typically there will be a high voltage between these two plates. Now, one of the good thing is that in electric field-based systems, we do not need ferrite. If we do not need ferrite, then of course it can be lighter. It can be easier to embed, as I already mentioned. Furthermore, it can be probably less expensive because if you see the material of this is essentially this insulation material and the copper plates and certain arrangements to put them together, which are all extremely low cost compared to lithium or compared to ferrite. There's a potential of having a better tolerance to alignment issue as well when the transmitting side and the receiving side are not aligned. This comes from the fact that a magnetic field has to start at one point and will loop back to the same point. So if the magnetic field is starting from here, the magnetic field line goes like this. And if the receiver comes within that, then only we will have some coupling. However, in capacitive technique with electric fields, it starts from the transmitter and the field lines end at the receiver from positive to negative. And therefore, as the receiver moves, the field lines get bent along with that. And therefore, the coupling can still stay at a high level, even with misalignment. So with these promises, again, we looked into this capacitive charging, and these are two test cases, but very typical example, not the most optimized example in either case. A comparison of weight of this coupler that will go into an electric vehicle versus that will go into a drone, these two applications. And we see that in both cases, the capacitive coupler is lighter compared to the inductive coupler. And the benefit is much more for electric vehicle because in this case, we use ferrite slabs. And in drone for inductive coupler, we do not use ferrite. So wherever we use ferrite slabs, of course, the benefit is much more. And even when we do not use ferrite only lithium, still there is a significant benefit in weight. Benefit in weight, of course, matters in EV, but probably matters even more for drone, where the drone has to lift along with that coupler attached to it. However, it comes at a price, and the problem for capacitive system is the following, and this is relatively a physical problem which cannot really be avoided. The physical problem is that the electric field by its nature can store a much less amount of energy in a given volume compared to magnetic field. The reason is, of course, the value of epsilon is much less than the value of mu. So that means that let's say we have this capacitive coupler versus inductive coupler in an EV with a certain area for these couplers. And there is a certain gap between the roadway and the vehicle. Therefore, within that volume, with that vertical gap and the area of the coupler, if we have electric field, then we will be able to store less amount of energy in the air gap. Versus in the inductive systems, we will be able to store much more energy in the gap. The solution to that is, however, is that it's not the energy that we store at a time, but power transfer depends on how frequently we transfer that energy to the output. We can store a small amount of energy at a time, but if we transfer that energy more frequently at the output, then we can achieve the same power transfer level. Therefore, to do that, what you have to do is for capacitive system, we'll need to increase the frequency much more compared to the inductive systems. And therefore, we'll need to operate the capacitive systems at multiple megahertz frequency. Inductive systems typically operate at tens of kilohertz, and capacitive systems will need to operate at multiple megahertz in order to meet the power transfer level. And the reason is that the energy density in the gap is much lower for capacitive. This is a typical architecture for a capacitive wireless charging system, where we have a DC input voltage, which can come from renewable energy, which can come from the grid after rectification, and we have a high frequency inverter. The purpose of this high frequency inverter is to convert the DC voltage into a high frequency AC because, of course, DC power can never go through a capacitor. So once we have created this high frequency AC, then we put a matching network over here, which is an LC network, which looks like this. And this has two purposes. One purpose is to step up the AC voltage so that we have a relatively higher voltage at this point. If we have a relatively higher voltage here, then we can transfer a higher amount of power with relatively small current, small displacement current through the capacitive coupler. A smaller displacement current will mean a smaller voltage across the capacitor and therefore smaller fringing electric fields around the coupler. And those fringing electric fields being smaller makes the system more safe. However, this is a relatively high voltage. The battery needs a relatively lower voltage, and therefore we have another network on this side which steps the voltage down. and then you have a rectifier which rectifies the AC to DC and then charges the battery. On top of that, these LC networks have another role to play, is that this capacitance is typically very small, of the order of picofarad, and therefore it has a very high reactance. So if we try to push power through this very high reactance, we'll end up having a very large reactive power and large voltage stress across the components. To mitigate that, this provides some inductive reactance that actually cancels out this capacitive reactance at this frequency, so that the impedance seen by the inverter looks resistive and we do not push reactive power, but only active power. So the purpose of these matching networks are twofold. One is to provide this voltage step up and step down so that we have a small displacement current and a small electric field across the gap. Another is to compensate for the reactance of the capacitive coupler. While doing this, while building this system, we have faced 4 major challenges. The first challenge is that since the capacitance is very small, of the order of few picofarad, there's overwhelming amount of parasitics in this system, which are of the order of this capacitance or even larger. And therefore, really trying to push power through this capacitance will also take into account power that are being transferred through the parasitics. The next problem is, of course, how to increase efficiency at such a high frequency. We are actually, as we see, we will be dealing with systems at 6.78 megahertz, one of the industrial, scientific, and medical band. So how to design the system so that we achieve enough efficiency at this point, at this frequency. As we keep increasing the power, we'll also see that the fringing electric field across the coupler increases, and that makes the edge of the car relatively unsafe. And therefore, we have to have a scheme where the power can be scaled up while the fringing field actually does not increase. So we'll discuss about that. And finally, we'll look into variations in coupling. This is a scenario that occurs in inductive or capacitive or any wireless charging systems invariably. And this can happen due to misalignment, that when the car is parked with a misalignment, or when in the dynamic charging scenario, the car is moving, there will be a misalignment between the transmitting and receiving side. It can also happen if cars with different ground clearances will come, for example, a sedan versus SUV, or there can be, for example, a water log on the street, or in cold places, snowfall on the street. Those will all change these capacitances, and therefore we will vary the coupling coefficient, and therefore we'll see that how to mitigate that. So the first thing is focusing on this parasitics. So a typical model of this capacitive coupler will be these 2 capacitors. That's what we'll simply think. Now, this is the vehicle chassis, this is the roadway, these 2 plates in the roadway, 2 plates underneath the vehicle chassis, and these are the wheels. So this is what we'll think. However, the vehicle chassis is metal, and if I put an enclosure around these plates, that will have a metal backplate. Considering those things are metal, we will actually see a capacitance between all metallic parts, and then it will look like this. Furthermore to that, if we have a rectifier PCB on the vehicle chassis and we have an inverter PCB on the vehicle chassis, the ground planes will create a further parasitic capacitance which look like this. So these 2 are the capacitance through which we actually want to transfer power, but there are several other capacitances around it. And if we look at it carefully, we'll understand that these capacitances are relatively small in value because the gap between these plates are large. However, the gap here is relatively small, so these capacitances are actually much larger. Therefore, if we do not take this into consideration, then pushing power through this will also mean power will go through all the other capacitances, which will reduce the actual power that will be transferred to the vehicle. So therefore, we have a need to consider all of these parasitic capacitances. So this is the model of the system, considering all of these parasitic capacitances and with these LC networks and inverter and rectifier on both sides. So if I actually see that particularly harmful are these capacitances, which goes from the roadway side to the inverter ground or the vehicle chassis to the rectifier ground. If I take this capacitance, then if there is a voltage across this capacitance, that will carry current back to the inverter, and that current is not going to reach the battery, and therefore it is going to affect the power transfer. So if I increase the values of this capacitance, we'll see that the power transfer falls drastically. even for a value of 10 picofarad of capacitance, which can easily occur between such things. So the way to eliminate this effect is to figure out a way so that there is no voltage across this capacitance, irrespective of the capacitance value. And since these are full bridge inverter and rectifiers, this can be done by splitting the inductors equally in the forward and return path, which will create zero voltage across these capacitances and effectively eliminate them from the system. And then whatever capacitance matrix we have left, we can do, and actually then we see that even with this capacitance values, the power transfer is independent. It's insensitive to those capacitance values. Then whatever part we have remaining, we can actually do two-port network theory to boil it down to a 4 capacitance model. Now, if you have an equivalent capacitance from here, and this equivalent capacitances all come from the parasitics, right? They're not external capacitors or physical capacitors, discrete capacitors that you put, but they all come from the parasitics of the system, of the charging environment. Then if we can control these parasitics, then we can actually eliminate C1 and C2, so that all of this required matching network capacitance comes from these values. And then we can merge these, and the way we can control the value of this capacitance CP2 over here is by controlling the gap between the plate and the vehicle chassis, and controlling the gap between the plate and the roadway, the frame of this coupler over here. So if I do that, then I can control the value of CP1, CP2, and I can make it such that these capacitances are what is needed in those LC matching networks. The benefit of that is that there will be no onboard capacitors, and that means there is no discrete capacitors on board, and it increases the efficiency as well as the safety of the system, because those discrete capacitors will have high voltage across them and will be prone to failure. Compared to not having them, will make the system much more robust. However, these capacitance and inductance values are of course very small and needs very accurate measurement. We can see that small error in measurement creates a large change in the power. And therefore, we have also devised certain methods to measure these model parameters more accurately. So if we have solved this, or not really solved this, but modeled these parasitics, all of these parasitics that are in the system, and we have come up with the 4 capacitance model, which we can use in our system design. Then the next question is, how much power can it transfer and at what efficiency? So the idea, if I go back for a minute, was that to absorb the parasitics into this modeling and then utilize these parasitics themselves for power transfer rather than using discrete capacitors. So utilizing this parasitic themselves will help us doing the power transfer. So this is the concept of this approach. So this network that we see over here, and we'll see how the power transfer and efficiency can be improved. We'll see that these shunt capacitances that we have drawn here are actually coming from the parasitics themselves. And these are not discrete capacitors, but from the parasitics, all of these 4. Now, what we can do is we can transform this pi network of capacitance that you see in the middle into a T network, and then we have a T resonant network over here. We can control the value of these inductances so that they have plus checks, minus checks, and plus checks values. If I do that and I see the output impedance looking from this port, we'll see that the output impedance is infinite. If a port has an output impedance of infinite, and if I draw the Norton equivalent of the circuit at this port, we'll see that it will look like a constant current source. If it's a constant current source, then while charging the battery, the charging current will remain constant. And that is something that we want, and therefore this network is designed this way. So the inductance values over here are chosen to meet this criteria so that we get a constant current over here, which is independent of the load, by making this output impedance infinite, and that provides a constant battery charging current. So this system looks relatively simple. So we have this inverter with 4 switches. We have the rectifier with 4 switches. This is something that we already talked about, how to get this part. The remaining part that we have over here is how to design these inductors. So before going there, a little bit about this inverter and rectifier switching. is that we know that there is switching loss when you switch a device because of overlap between transition in voltage and transition in current. Okay. And the loss that we occur typically is what we call the hard switching loss. So this shows the hard switching loss in these devices at a frequency of 6.78 megahertz. And you see that with increasing blocking voltage of the device, the switching loss per device can go well above 100 watts, which for wide bandgap devices is quite large. For example, to design this at 6 megahertz, we use gallium nitride devices, and the gallium nitride devices can typically withstand a very low amount of loss, not, of course, beyond 100 watts. So there is a soft switching requirement where the voltage and current transitions can be separated out, and these losses can be eliminated. The way to do that is to add these shunt inductors across the inverter and rectifier, which then provides the current that is needed to discharge the output capacitances of the switches. And this is the additional charge that we get due to the current in these ZVS inductors, which helps us achieve soft switching. So this is a modification that we do in the circuit in order to achieve soft switching of the inverter and rectifier, because soft switching is not only will reduce loss, but if I do not soft switch, then that is a thermally prohibitive at this frequency and the system will not work simply because of thermal reasons. So now we go to the inductor and we see how to efficiently design these inductors. Now, one of the things is that typically at lower frequencies, we use core, and on top of that, we use lead sweat to wind the inductors. But the core loss increases exponentially with frequency. And if we see at this 6 megahertz level, then this frequency becomes, this loss becomes too much. And the inductance value can be relatively low because the frequency is high. So it may be possible to completely eliminate the core and use an air core design. So that is what we have been exploring. And one of the air core designs is, of course, to make them on a toroid, and another air core design is to wind this on a solenoid to make the inductors. The trade-offs are that if I make it a toroid, then the flux is all contained within the toroid mostly, and less flux is fringing out, which is good for metallic systems around the inductor. That means less eddy current losses. However, this increases the inter-turn capacitance because we see that these turns over here comes very close to one another. And if this inter-turn capacitance is increased, that increases circulating current between the turns, which effectively increases loss. On the other hand, if we go with solenoidal inductors, we'll have more fringing flux because the flux has to come back from outside. But we'll have a lower inter-turn capacitance and therefore lower circulating current between the turns and therefore lower losses. So we'll explore this solenoidal inductor a little more in this subsequent slides. So let's say we have chosen a solenoidal inductor. Now the next question is, what is the type of wire that we'll use? One option, of course, is to use lead wire, but we have already known that lead wire does not work very well at these frequencies and becomes extremely lossy due to proximity effects. So one option is to use a rectangular cross section, kind of a foil wire, which can be used. And if I use a foil wire and see its cross section, then it looks like this, where these brown portions are the current within that cross section area. Why the currents look like this is because of skin effect, that at this high frequency, the current moves to the skin of the conductor. One of the ways to actually utilize it better is to roll this foil and make it a circular cross section. Of course, if I roll this foil, then it will look like a hollow circular cross section. But the good thing is that then for the same width over here, the circular cross section will have a pi times higher area. And the current density will look like this. Now, if I see here, the current goes to both sides. Here, the current is only in one side. So that provides a factor of half, and therefore an improvement of pi over 2 in the AC resistance. So going from this rectangular to hollow circular gives us an improvement of pi, but this current density reduces the improvement by a factor of 2. So overall, we have an improvement of pi by 2 in AC resistance, which is still significant, which is more than a 50% improvement. Now, next, what we want to see is that, okay, let's say I choose this hollow circular wire, but what will be the distance between consecutive turns from one turn to another, and how does that affect? So what we see is that if I have more intertrans spacing, then the AC resistance reduces a lot. And the reason is that if I have less intertrans spacing, then there will be more induced eddy current in those adjacent wires due to the current in one of those turns. So you have more eddy current induction to the adjacent wires, leading to higher loss. And as the spacing increases, we have lower eddy currents in this due to the other turns, and therefore it kind of settles at one value. After a certain point, of course, there is no proximity effect between the turns if the spacing is too large, and then this settles at the value where the skin resistance will be. We have also compared the rectangular and the hollow cross section, hollow circular cross sections over here. We see that after certain spacing, the hollow circular cross section has a much smaller AC resistance compared to the rectangular one. However, one of the problem is that if I increase the spacing to reduce loss, that means the coupling between the adjacent turns are also reducing. If the coupling between the adjacent turns reduces, that will reduce the inductance value that we achieve from this structure. So we want to maintain a constant inductance value, but we want to reduce the AC resistance. If the inductance reduces and we want to maintain a constant inductance, then we need to put more turns. If I want to put more turns, then that increases the AC resistance again. So there seems to be an optimal point as indicated in this plot. Over here, we have higher proximity loss between adjacent turns because of low interturn spacing, and therefore the loss increases. But as the inductance reduces with interturn spacing, then to increase the inductance, we need more amount of turns, which increases the loss over here. So there is an optimal point in between where the AC resistance is minimum. And with that optimal spacing, then with the hollow circular cross section where we have built this inductor, where these are the specifications that we have. Now, using this inductor, finally, we have built this prototype capacitive system, which currently works at 1.8 kilowatt power transfer at 6.7 megahertz. The gap between the transmitter and the receiver side is 15 centimeter, which is typically the air gap, that with the ground clearance that we see in cars, in four-wheelers. Right now, we have 84% DC to DC efficiency. And of course, in this project, the goal is to improve this power transfer and the efficiency both. This shows the transmitter side and receiver side plates, which are implemented here inside printed circuit boards. And these are the waveforms at 1.8 kilowatt. Now, of course, we try to improve the power because 1.8 kilowatt is not good enough to charge an electric vehicle. We'll at least want to go to 3.77 or 11 kilowatt and so on. If I try to improve the power, try to increase the power, then what is going to happen is that the voltage across this plate from transmitter to receiver will increase, which will create a higher fringing electric field around this coupler. And that will make this system unsafe because consider a system that these plates are underneath the car and someone can go to the edge of the car to enter the vehicle when the car is charging. Therefore, if I walk up to the edge of the car and we have a lot of fringing electric field around this coupler, then these electric fields will penetrate the human body, and therefore that is not desired because that is not good for human tissue. So we want a solution over here where we'll restrict the fringing fields, but we'll be able to scale up the power. So we want to increase power, but restrict the fringing fields. In order to do that, we can take a modular approach. In this modular approach, the power of each of these modules are added up. But each of these modules, the adjacent modules, are operated with 180-degree phase shift so that their fields are in the opposite direction and they cancel one another. So with this 180-degree phase shift between adjacent modules, what we do is that their powers add up, but their fields cancel. Therefore, we can scale up power, but the fringing fields will not improve. We will not increase. And therefore, this is one of the promise and which we are going to explore further in this project. Now, we have looked into certain modular structures as well, where this is one of these two module systems where you have 4 plates on each of the sides. And we see that the capacitance between the inner plates is relatively low here, and the capacitance between the outer plates is relatively more. The reason is that the fringing is possible in the outer plates, which increases the capacitance. Therefore, we need to select the plates that we use for one of these modules very intelligently, so that within a module there is no asymmetry and the capacitances are equal. So let's say we have chosen them that way, but even after we have done this, we'll see that there are a lot of interaction between the modules. So if you remember, this was the initial set of parasitic capacitances that we boiled down to 4 capacitance model. This is for module 1. Module 2 has the same set of capacitance that we can boil down to 4 capacitance model. However, there are these intermodular parasitic interactions through all of these capacitances, which now we need to take care of. To do that, we have figured out that there is a very interesting benefit that we can get if we create this 180-degree phase shift between adjacent modules. Because 180-degree phase shift, then we can intermodular parasitic capacitances into 2 categories. And you see that for one of these categories, the potential difference across the capacitance will always be 0, which means that there will be no displacement current flowing through those capacitances. There will be no, these capacitances are not connecting the 2 modules. There is another type of reaction where the current leaving one of this module to the other is the same as the current going back. And therefore, this is a current loop between these 2 capacitances. And therefore, this can be split and be modeled individually into these 2 modules separately. What this does is that this allows us to either eliminate some of these interactions or model some of these interactions into the individual modules rather than between the modules. So if I do that, then all of these parasitics can be modeled in a decoupled way, where of course this capacitance value and this capacitance value, they are different and they depend on the values of these interactions. So we have simulated this and we have seen that with the decoupled module, the power transfer is constant, whereas if I do not decouple, then the power transfer falls drastically. So this method means that we have a modular approach. We have a 180-degree phase shift between adjacent modules. The power improves, the field cancel. The 180-degree phase shift also helps us decouple the 2 modules, and therefore we can then design each of these modules individually, and we can get a constant power transfer. So this is a 2 module we have also tried, where you have achieved 3 kilowatt power transfer at 85% efficiency. And these are the waveforms of the 2 modules. And we can see that from these transitions that we are achieving soft switching at 6.78 megahertz. And we see that very similar power transfer in both the modules. That means they are symmetrically sharing the power and therefore symmetrically sharing the voltage and current stress across the elements. A field measurement with the modular system is still to be done, and we'll see whether the field has reduced or not. But the promise as per simulation is that it should reduce. So we have gone through these 3 things. So if I summarize at this point, just a minute, is that we have overwhelming amount of parasitic capacitances that reduce the power transfer. We model them first to split the inductor to get rid of certain capacitances. Then we model the remaining capacitances and the 4 capacitance model that we can utilize. Then we said that, okay, we'll adjust the gap between the plate and the chassis or between the plate and the roadway so that those capacitances can be used for power transfer itself rather than trying to eliminate it. So once we have done that, then we looked into this inductor design and we saw that a hollow circular cross-section based solenoidal inductor with an optimal intertrans spacing gave us a high efficiency. We tried to improve the power, cancel one another, and therefore you can increase power safely. One of this, now the last that we try to tackle over here is the variations in coupling, as I said, and they are independent of inductive or capacitive system. As I've already mentioned, that it can happen due to misalignment between the 2 sides or having cars with various ground clearances, or of course the presence of foreign objects like waterlogging or snow on top of the roadway, or somebody throws a can of soda. That will also change the capacitance between this. The traditional ways is that if the capacitance changes, then we are no more in resonance. And therefore, you change the frequency to get back into resonance and therefore get back power transfer. But the frequency that we operate at is called the industrial, scientific, and medical band of frequency, which has a center frequency of 6.78 megahertz with a band of around 50 kilohertz around them. So the amount of change that we can do on top of 6.78 megahertz is very, very limited. So essentially, we have to operate at a constant frequency. Therefore, the frequency variation method of tackling this is not possible in this system. Another way is to keep the frequency same. The capacitance is changing, therefore change the inductance to restore resonance. To do that, we'll use various switches across these inductors, and therefore we can change the value of the inductance, how much inductance is there in the system at a time. The problem is that this method is granular. That means you can only add certain amount of inductances at a time. And the next thing is that we'll need many, many switches if we want to make it very smooth, the change in inductance. And all of these switches will have a very high voltage blocking capability, need to have, because these inductors are resonant inductors and will have a large voltage across them. So this does not look like a solution that is really scalable to higher power, because the higher power means very, very high voltage blocking across these switches because they are across resonant inductors. So what we proposed is what we call the active variable reactance rectifier, where we operate at a fixed frequency, but we provide a continuous compensation. It's not granular in nature, but continuous. What we do is we split the power into two branches, one which goes to an inductive branch, one which goes to a capacitive branch. And then we rectify those powers, and then we feed it through two DC-DC converters, which then combine to a DC power at the output to charge the battery. Now, at nominal situation, these matching networks, the LCs, they actually compensate for this coupling capacitance, and therefore you see a resistive impedance here, no reactive power. But as soon as there is this capacitance change due to coupling variation, we see a reactive power coming from here. So at that point, what it does is it changes the ratio of power that goes into these two branches by controlling the values of V1, V2. So if I make V1 and V2 different, then maybe more amount of power can go to the inductive branch compared to the amount that goes in capacitive branch. So if there is an unequal power distribution between the inductive and capacitive branch, then overall, I'll see an inductive or capacitive reactance, which can then compensate for the change in this coupling reactance, and therefore we can eliminate the reactive power. So all we need to do here is to control the values of V1, V2 by controlling the duty ratio of these DC-DC converters to make sure that the reactive power has gone down to zero. So this is what the plot shows, is that with no misalignment, we have the voltages equal. With misalignment, they change both of these voltages. With changes the power transfer through both of this branch, but the overall power transfer remains the same. So with this AVR rectifier, we have done this experiment where we have seen that the power remains constant for up to 45% misalignment. However, this limitation of 45% or 50%, whatever it is, comes from the system specifications. So by this AVR rectifier, if we have a certain systems with a certain specifications, we won't be able to go beyond this. To mitigate this, then we made a couple of changes. We changed these inductive and capacitive reactances over here in the two branches. We introduced this factor alpha, which essentially captures the relative value between these two reactances. And we made a topological modification, which is shown over here. If we do this, then it can be shown that we can provide a much higher reactance. And this is how much compensation we can give is actually independent of system specifications. So now the coupling variations can be much more, and we should be able to compensate for that by providing enough reactance from this circuit. So this is what it shows. This line is for AVR, which depends on the system specification. And this line is for the proposed circuit, where it is independent of system specifications and can maximum go to this. These are the experimental results. So we see that with AVR, we are able to go up to this much change in reactance. With VCR, we are able to go to double the change in coupling reactance. That means much more misalignment can be mitigated. Now, why do we care about much more misalignment or much less? Of course, from a static charging point of view, if the car is misaligned more, then I can still charge it at the same rate. And from a dynamic charging point of view, where car is continuously moving, we can keep pushing the same amount of power for a longer duration. And if I can do that, then more amount of power goes from each of the charging pads. That means we need the next charging pad further apart. That means the charging pad's frequency in space will be smaller, and therefore we need less amount of charging pads to be embedded. That reduces the infrastructure cost to start with for dynamic charging scenario. So that's the work, and these are the references for this works. Looking forward in this project, the first objective we have is to scale up power and improve efficiency. We are targeting 7 kilowatt of power at more than 90% DC to DC efficiency. And the way to do it is, of course, to reduce the inductor losses, because that's the main source of loss. The inductor size will also need to be reduced because the air core inductors are typically a bit larger in size and may not be viable to be implemented within the vehicle. We'd also need to ensure soft switching as the operating conditions change due to misalignment, due to load variations, and so on. Otherwise, this will be thermally prohibitive. So this is as far as this project goes, where we are trying to improve power efficiency while reducing the fringing field and also tackling the misalignment or coupling variation issues. Now, if we take our perspective a little further away, we have now two systems. One is inductive system, where the research has happened for a longer period of time, and therefore it has been developed a little relatively more with higher power transfer and efficiency. Now we are trying to develop this capacitive system to achieve similar level of power and efficiency, and we are at the research stage. The benefit of capacitive, the promise is that we will be able to use couplers which will be easier to embed in the roadway and which has less weight and therefore add much smaller weight to the car. Now the question is then which one is better, inductive or capacitive? And that is one of the directions of research that we have, and we're trying to find the answer to. And it may also be that the inductive or capacitive, none of this by itself provides all the benefits, and in which case we need to explore some hybrid system which combines the benefit of the two. It can also be that for different applications, one can be better than the other. Maybe for EV application, one is better. Maybe for drone application, one is better, and so on. So this is something that should be in perspective and something that should be thought of as well. So that is the end of my talk. So thank you, everyone, and I'll be ready to take questions. Ms. Maitti, if you are speaking, I think you were muted.
So recording will be available on our YouTube channel. The link of YouTube and LinkedIn is available on the chat box. Any doubt? Okay, Professor.
Okay.
Thank you so much for this insightful session.
Sure.
Thank you for
Thank you.
giving this session and join with this series, eRides webinar series. And thank you all the participants who has joined this session. So every month we will be conducting webinar on this in the subject of e-mobility. So please join in further webinar series also.
Okay. Thank you.
Thank you so much.
Thank you.
Thank you.